Okay, we're going to be looking at different counting methods in this lesson. The first thing we're going to do is going back and reviewing something that we did earlier in this chapter with the fundamental counting principle. Problem number 1, determine the number of possible outcomes for tossing a coin and rolling a die. You have two different outcomes for tossing a coin, either heads or tail. When you roll a die, you have 6 different outcomes. So when we multiply those two together, we get a total of 12 different outcomes. Problem 2, determine the possible number of outcomes of choosing 2 letters followed by 2 digits. Repetition is allowed. A lot of students like to make these little blanks here to kind of help them organize their thinking. I've got 26 letters in the alphabet, so I have 26 choices for that first slot. If repetition is allowed, I have 26 choices for the second slot. Now these next 2 spaces need to be followed by digits. So I've got 10 choices here and 10 choices there. So I have 67,600 different outcomes. Problem 3 is very similar to problem 2, but here repetition is not allowed. I still have these 4 spots that I need to fill. Got 26 options for that first slot, but only 25 for that second slot. These last 2 slots are digits. I have 10 options here, but only 9 options here. So that will give me 58,500 different possible outcomes. Why don't you pause the video and see if you can do problem number 4 on your own. Okay, here's my answer for problem 4. Now let's work through problem 5 together. Anne must create a 4-letter password. So again, I have 4 slots here. The first letter must be either A, B, or C. The last letter cannot be X, and repetition is allowed. How many different passwords are possible? Okay, the first letter has to be A, B, or C. So I have 3 options for that first spot. Since repetition is allowed, I have 26 options for the second slot, 26 options for the third slot, and this last letter cannot be X, so that leaves me with 25 options here. So that's going to give me 50,700 outcomes. Problem number 6, how many different gender sequences are possible for 6 children? 3, 4, 5, 6. Don't get this problem confused with the probability of getting, like, say, 6 girls in a row. This is asking us how many different sequences there are. You know, if it's girl, 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 boy, 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 or girl, boy, girl, boy, girl, boy, you know, that type of thing. So there are 2 options for my first child, either boy or girl. And for the second, and the third, and the fourth, and the 5th, and the 6th. So there are 2 to the 6th power options there, or sequences, and that is 64. Pause the recording and see if you can figure out number 7 on your own. Okay, the answer to number 7 was 32. Now we're going to look at different types of counting methods, permutations and combinations. Now, they both have this in common. They represent the number of ways we can choose R objects from n possibilities. For example, if I have 10 things and I'm going to choose 3 of them. All the selections come from a single group of items. No item may be selected more than once. Okay, so repetition is not allowed. The difference between a permutation and a combination is whether or not order matters. The order of arrangement matters, it's permutation. The order of arrangement does not matter, it's a combination. And we can see an example here. With a permutation, ABCD is different than DCBA, but with a combination, they're going to represent the same thing. Now we also have a couple of formulas written out here, and these formulas are also on your reference sheet, but know that you do not really need to know these formulas here. You can just use your calculator to put the problems in like this, and you're going to get your answer easier that way. And everybody has a different calculator, so please refer to your owner's manual for your calculator on how to use these keys. One thing that all calculators are going to have in common is that this first number here is representing how many different items that you're choosing from, and that second number is how many different items you're choosing. So in this problem, I have 15 different items that I'm choosing from, and I'm going to select 9 of them. And with its a permutation, the order matters. So what I want you to do is to pause the video, stop here and work through these problems with your calculator, and be sure that you know how to use your calculator. And we'll come back and check your answers. Okay, there are your answers. One thing I want to point out here is that problem 2 and problem 3 are very similar. I have 10 items that I'm choosing from, and I'm choosing 3 out of the 10. With problem 2, the order does not matter. In problem 3, the order does, and you can see I have very different answers there. And when you have a situation like this, when you're looking at the same numbers, a permutation is always going to have a larger number of outcomes than a combination. Okay, so going on to problem number 7. How many different 4-digit PIN numbers are possible if numbers cannot be repeated? There's a couple of different ways that I could think about doing this problem. One way is to think about it like I have done the other problems. I've got 4 different slots I have to fill. I've got 10 options for that first slot. Numbers cannot be repeated, then I only have 9, and then 8, and then 7. And I can multiply all those together. Another way to think about this is realizing that it is a permutation. I've got a group of numbers that I'm choosing from. So I'm choosing from one group of things. I cannot repeat my selections, and the order matters. So I've got 10 things that I'm choosing from, and I am choosing 4 of them. Either way that I do the problem, I get the same answer, 5,040. Problem 8, how many flavor combinations are possible if you choose 3 out of the 12 flavors? I'm choosing from one group of things, and repetition is not allowed. And the order does not matter. So I've got 12 things I'm choosing from. It's a combination because order does not matter, and I'm choosing 3 of the 12. That is going to give me 220 different answers, or 220 different combinations. All right, problem 9. A middle school principal needs to schedule 7 different classes: algebra, English, history, Spanish, science, study hall, and gym, in 7 different time periods. How many different class schedules are possible? I could think about this problem in a couple of different ways. I've got 1, 2, 3, 4, 5, 6, 7 different slots to choose from. 7 options for that first slot. Now, once I choose, say, algebra for that first slot, I'm not going to choose it again. So now I only have 6 things to choose from for the second slot, and then 5, 4, 3, 2, and 1, and I can multiply all of that together. Another way to think of this is that I'm choosing from one group of things. Repetition is not allowed. So it's either a permutation or a combination. And since the order matters, it is a permutation. I have 7 things to choose from, and I'm choosing all 7 of those. And that's going to give me 5,040 different outcomes here. Okay, problem 10 and problem 11 kind of go hand in hand. Problem 10, Lily wants to buy 3 new paintings to put in her office, and she has 8 different paintings to choose from. How many different groups of 3 paintings can she create? And problem 11, Lily wants to buy 3 new paintings, and she will put 1 in her lobby and 1 in her hallway and 1 in her office. She has 8 paintings to choose from. How many different options does she have for hanging the 3 paintings? So on both of these, I have a group of things that I'm choosing from, and I've got 8 in that group that I'm choosing from, and I'm choosing 3 of the 8. Repetition is not allowed. What we need to decide here is whether they are permutations or combinations. If I am looking for just a group of things, then it is a combination. If order matters, it's a permutation. And here's what is really important about this. It's not necessarily that I'm hanging the painting in the lobby first and the one in her office second and the hallway third. It's just that each of the paintings are assigned a different role. So when our reference sheet says that order matters for permutation, it doesn't necessarily mean first, second, third, but just that each thing has a certain role that they're playing. So this is a permutation. So here I have 56 different groups, and here I have 336 different ways that I could hang the paintings. Okay. Going on to problem 12, how many different passwords can you create from the letters in network if all the letters must be used and repetition is not allowed? Now I can do this type of thing here. I've got 7, 6, 5, 4, 3, 2, 1. Okay. But I should also know that because I'm choosing from one group of things and repetition is not allowed and order matters, because it's a password, order matters, that this is a permutation. And I'm choosing from 7 different letters, and I'm choosing all 7 of them. So I have 5,040. Now, one thing I want to point out about this word here, network, is that all of the letters in network are different. I couldn't do the problem this way if I had any of these letters repeating, because let's say the E repeated. Well, it wouldn't matter which E I chose, it would still spell out the same word. I believe there are some problems like that in our book that are shown, but we're not going to get into any problems quite that complicated in this course. All right, next problem. Bobby's going to select 3 spices to put in his chili. He has 10 spices to choose from. How many different flavor combinations can he make? He's got 10 to choose from, and he's choosing 3. So I have to figure out whether it's a combination or a permutation. And order does not matter, right? Unless it's Bobby Flay, who's a chef, who would probably tell you that there's a certain order that your spices have to go into the chili. But we're just going to say the order does not matter. So that is a combination. And that's going to give me 120 different options. Now, I want to point out something about the word combinations here. Just because we see the word combination sometimes in our everyday life doesn't mean it's necessarily mathematically a combination. It might actually be a permutation. And there's a bad math joke about a combination lock should actually be called a permutation lock, because your combination to your lock is actually not really a combination. It's really a permutation because the order matters. All right, problem 14. Ellen has 8 Dr. Seuss books. She's going to select 5 of them to donate to the library. How many different groups of 5 books can she create? Well, it's just a group of 5, so that's a combination. Each of those books are not doing anything in particular. All right, let me give you a chance to pause this and do the next 3 problems here on your own. Okay, there are my answers for 15 through 17. Problem 18 and problem 19 are going to sort of go together. Problem 18, a city council has 10 members and they must select a 3-person committee. How many different subcommittees can be formed? Problem 19, suppose you have 10 candidates running for a 3-person committee where the top vote becomes president, the second is vice president, the third is secretary. How many different ways can you choose 3 from the 10 candidates? Both of these problems I'm choosing from one group and repetition is not allowed. I'm choosing from 10 options from 10 people, and I'm choosing 3 of them. With problem 18, I'm just choosing a committee. I just want a group of 3 people. That is a combination. Down here, I have a vice president, president, and a secretary. So each person is assigned a certain role. That is a permutation. So up here I have 120 different groups, and here I have 720 different ways that I can get those 3 people into those 3 offices. Problem 20. How many 5-letter passwords are possible if letters can be repeated? So this actually goes back to our fundamental counting principle. This is not a permutation or combination, because remember, with permutations and combinations, repetition is not allowed. Here, repetition is allowed, so I have to use the fundamental counting principle. I've got 26 letters to choose from here, and here, and here. Each slot has 26 different options. So that's 26 to the 5th power. So that's 11,881,376. And problem 21, how many different 5-card hands can be dealt from a 52-card deck? I'm just looking for a group of 5 cards. Order does not matter, so it is a combination. So 52 is how many I'm choosing from. I'm choosing 5. There's going to be 2,000,000 598,960 different hands that I can